Let's start again. So I hope you are well rested. This is the part where we construct the thing finally. So you have to be sharp, okay? You have to be sharp. So again, we are being very anachronic. We are constructing tensor network states in a modern way with PEPs, which means you will understand the name: projected, entangled, pair states. And this idea from Verstraete and Sirac from 2004. So it's basically when people understood that this tensor network philosophy was not restricted to 1D with the MRG, but was general to arbitrary dimension. So I mean, then we could have introduced everything from the perspective of MPS first. What I will do is a bit different. We will start sort of general in dimension, and then we will specialize to MPS, even though we won't do algorithms in general dimension. But I think it helps to be in a fairly general context first. OK, so my objective is to construct a state psi that lives in a physical Hilbert space. So the Hilbert space of my theory, that's a product of tensor of factors. That's a tensor product on sites. And I'm going to assume it's CD, so script D. So I allow Q dits now. And I will try to be careful to distinguish this D from the capital D, which is going to be the auxiliary. This is probably an unfortunate notation, but it's the one of the literature, so I will use it. Let me write the points of my lattice. And if I write too many, it's going to be a pain to draw the rest, but I will. OK, these are my lattice points, and that's where I have my spins. And now what I'm going to do, I'm going to start by tiling this space with entanglement. Okay, that doesn't really mean anything. I'm going to put pairs, entangled pairs, between sites. So since I'm in 2D, each site is going to get 4 half pairs. Okay? This is unrelated to my physical theory. I'm sort of making an entanglement carpet or whatever under. OK, you get it, but I have to. What this pair means is a maximally entangled state in capital D dimensions. So it's a state, this pair has more and more entanglement if I increase the dimension, OK? So far, this is pretty weird, and I am, let's call this guy psi L. And this L is like it's a bond index. OK, so here, these two states, they live on one site or the other, but the state as a whole really lives on the bond. It's associated to each bond. OK, this is an abstract definition so far, and I'm constructing a sort of auxiliary state that has nothing to do with where I want to go, so it's worrying so far. That is the tensor product over all the bonds of this psi L. Okay, so I constructed a sort of weird Hilbert space where now for each site I have 4 sites, and now I have this kind of entanglement pattern. So you see this auxiliary state by construction is a state that has local entanglement, verifies the area law, but it's a very trivial state. And now what I will do is I will introduce a linear map on each site now. Linear map, let's call it A of x. So I will call my site x. And this linear map is going to bring me from the wrong auxiliary Hilbert space to the correct one. So it's a map that goes from CD, tensor CD, tensor C capital D, tensor C capital D, and goes to CD.
So Antoine, before going,
yeah.
Can you explain again why this auxiliary state is it has local entanglement and it verifies the other law? I don't see it.
I mean, intuitively, at least, if you start to cut, the entanglement is proportional to the number of bonds you cut.
Okay.
So the entanglement of a region with the rest is proportional to how many bonds you cut, so roughly to the area in the sense of perimeter here.
Yes.
Again, as long as you don't make the surface weirdly fractal or anything.
So
yeah.
for a small L is numbering the edges?
Yeah, the bonds, what I say, really edges is better. Okay. You're right. Edges. And x here is the site. So I'm defining as many linear maps A of x as I have sites. And what this linear map does is it takes 4 states in the auxiliary Hilbert space, so 4 half pairs, and maps it to one state in the original Hilbert space. So pictorially, usually we write it like this. This is your map A. Okay, and this is A of x, but on each site. Okay, and this is a linear map, but sometimes you have to think this is a big space, and we go to this is a big Hilbert space. We go typically to a smaller Hilbert space. We call it a projection, but it's like the usual sense. Okay, we are projecting. So we have entangled pairs of states. Okay, it's one part of the name, and then we project them back to the original Hilbert space. Okay, so right now, this is, I didn't really define the state. I will define it here formally. I defined it with words, but now what the state I call psi A is the product for all x that's a site of, I'm not good at this, okay, of the A of x applied to the state okay. This is, again, if I wanted to write it precisely with the indices and stuff, it would be a bit tricky. But we understand that the A is really associated to each site and takes 4 of these and maps it to the original Hilbert space. So I just wanted to be clear. That's where you have to check if you understand that this is indeed a state in the physical Hilbert space. And that's called the PEPS. And in fact, it's already a tensor network state. Okay, so how many free parameters do we have? So A is a linear map from CD, D, 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 capital D to script D. So, and we have n of them because it's potentially a different map on each side. So A contains arbitrary, so the free parameters. And we have n times d4 times d parameters. And of course, here it would be d squared in 1D, and it would be d6 in 3D. So this is because I make my drawing in 2D, but I mean, you should understand that this construction here, you should understand what's specific to the fact that I'm in 2D. The fact that there are 4 on each side is really specific to 2D. It would be only 2 in 1D, but other than that, it's... Okay, so that's the tough part. We introduce these auxiliary states that are entangled, and now we locally map these 4 pairs to the physical space. Yeah?
I'm not sure, because psi L doesn't live in the right space. Right?
Yeah, so this,
how can I understand
this does not, but this linear map is this. So this is a linear map that brings it to the right Hilbert space.
So it's A of X of the state.
So it's the, okay, I should maybe have done something like that.
A is tensor identity and then you multiply.
Or you write it like that, it's okay. So if you do a tensor product, okay, I assume that sort of I was taking A, what I was doing the identification, A of X is the same as A of X on its subspace and then the identity. So I wrote it as a product, but probably it's better to write a tensor product as well. So this operator here is really taking all on each block, bringing me to the right Hilbert space. So overall, it's bringing me to the right Hilbert space. Yes?
So, psi A is the tensor product of these 2 big tensor products.
Say again?
Like, actually, there's a tensor product between the 2 bracketed tensor products.
No, so this is an operator.
Yeah, between the closing and the opening brackets and parentheses. Just with the L and X things.
Here, this is separate. This is a quantum state.
Yeah.
The whole thing here is a quantum state. This whole thing here is an operator acting on this quantum state.
Oh.
Okay. I agree that it's tricky. We will see that at the end of the day, we always write it graphically because it's a mess otherwise. But I have to show the construction, and then quickly we're going to do only graphical notations. And at first, it's going to be even worse, but long term, it's going to be clear. Okay, but just to understand the construction, and again, so we put these pairs on the lattice, and these pairs, you see, they have an arbitrary parameter, so they sort of control how much free entanglement we are going to be able to harvest in our state. And then these maps are arbitrary, and these are the things precisely we are going to optimize. We are going to optimize over all these maps to find the best energy, typically. So these are really the free parameters are these maps. But these maps are really just coefficients, okay? You could, they are just, it's a big matrix from this to this, a big rectangular matrix. Okay, all good? So we are right now doing the tricky parts, I would say, of the construction. Yeah.
The L linked to the edges is not dependent on the X or on the A.
No. So you first construct the state where I had not drawn any orange circles or anything. So it's a state living in this auxiliary Hilbert space. And then only after that you apply the A of X. Okay, why? I mean, why you? The only way to really see what's going on is to make a drawing, because you see the way these pairs are. This state psi L is defined for a pair, and the way I'm grouping them is taking 4/2 of a pair. So it's hard to get a feeling without really writing the drawing of what is associated to what. Okay. It's going to be clear in 1D, but okay. And this is the time when we do a technical aparté on tensor network notation to sort of simplify our lives a little bit. But maybe if there are questions about what the state is right now and what's the philosophy. Okay, long term, what we want this psi A is we want to be able to evaluate, say, the Hamiltonian on it and then minimize over all these linear maps. That's easier said than done. We'll do it later. But if I want to make sure you understood what it is that we just did and what we now want to do. Yes? On 4/2. Yeah. Here, these are the Hilbert space of halves, of the 4/2 that are here. So if I took this example, it's really these 4/2 here. Yeah.
The little d here, like this is not the dimension anymore.
So the small d is the physical dimension you have on each side. You can think it's 2. It's not the thing that scale. It's 2 if you like. I mean, the construction is fully general, but it's 2 for spins. Okay, and it doesn't have any. We're gonna lack a letter for space-time dimension, but okay, it's gonna be clear given the situation in which case we are.
Is this the small d or the big d?
So nothing here is the space-time dimension. Here it's fixed to 2 in the drawing. What is the capital D is this auxiliary dimension controlling the number of free parameters. It's the size of the variational manifold.
But because when you draw like the bell curve and
Yeah.
then you write it is equal to k from 1 to
Yeah.
capital D.
Yes, this bell pair doesn't live in the physical Hilbert space. This bell pair is an auxiliary state. It belongs to this auxiliary Hilbert space. And the role of the A is then to map that back to our physical Hilbert space.
Okay.
So it's arbitrary, D. I mean, the capital D is arbitrary. The larger it is, the more parameters we have, it's clear. Also, the more entanglement we have that we are going to be able to use. So intuitively, the more the state is expressive, the more we are going to be able to approximate. Yeah?
What is n again, capital N?
Sorry, I think never introduced it, but for me, capital N is the number of sites, usually. So the size, system size.
But a single map contains d to the 4 times d, right? And there is n.
Yeah, but I have n of them, so the number of parameters is n times d4. Yeah, okay. Okay, I should say this is in many cases, we're interested in translation invariant system, in which case this n disappears, so we don't have more parameters, but okay, let's, actually DMRG in its standard incarnation is site dependent, so it's, but you have to see this linear cost in n is nothing. It's like, usually it's exponential. So here it's like, and you see you can do, I mean, if your algorithm can do 100 sites, you can do 1,000 sites but with 10 times more time. It's nothing, okay? Okay, and I should say, intuitively at least, will be a bit clearer later, but this state still projected will verify the area law, okay? Because what I did, I started from entangled pairs. In this auxiliary Hilbert space, it's clear I verify the area law, right? Before I do any type of mapping. And then I'm going to do only local mappings. These local mappings, they won't be able to increase entanglement, so this is clear intuitively. Again, I will be more precise later that this should have the right properties, okay? Okay. And the fact that n is in front here is also a sign that we have an extensive parametrization. You see that the cost of parameterizing the state is really independent. I mean, grows only linearly with system size, not exponentially. Okay, I keep on, and now we have to do this aparté that I've been selling you for a while. Tensor network notation. So we're going to work with this object is already can be seen as a tensor. It's an object living in sort of either. Let me let me not fast track it. Tensor network notation. So you can make a mistake at that stage and try to rephrase as much as you can in the old language and resist the notation for as long as possible. And in the matrix product state case, it's actually possible. That's why I started in the complicated case already, so that it's harder and so you're not tempted to do it. Because I, for example, wasted a lot of time always going back. And okay, so I'm sorry, but it's clearly better. And so you have to work this way. So it's a notation for a linear algebra with tensor. So there is nothing fancy about it. We're just, OK. Actually, why it's going to be tricky at the beginning is if you are, in a way, if you are too rigorous about math, it's going to be worrying because we're going to identify Hilbert spaces and their duals all the time because we are in finite dimensions, everything is all right. So for me, I should say also tensor here is going to have no link whatsoever with differential geometry, contravariance, covariance, whatever. You don't care. You can put the indices up, down. It doesn't mean anything to me. For me, they are a NumPy array. Okay? So you should really think of a tensor as a NumPy array. It has no additional structure at this stage. Or whatever, okay? A Julia array, I'm fine with it too. Okay? So in a basis, it's like that. But for me, the vector is just the coefficient here. Okay? And that I will write v and something like this. And at the beginning, we write v inside the ball, and we write the k here. And at the end, we will write nothing. But OK, it's the beginning, so we are. Then a matrix. OK, this is this kind of explanation where everything looks trivial at first. I'm going to put a hat to show it's really an operator. That KL, and the matrix has coefficients. And in a basis, it's something like this, OK? But actually, for me, it's the same as a vector living. Since I care only about the coefficients, for me, it's the same as a vector living in two copies of the Hilbert space, OK? I just reversed Bra and Ket here. For me, it's the same object. And that I write like this. OK, so here you see that deep down, I'm not caring whether a thing is the space, it's dual, whether I'm talking about form or vectors. And that's precisely what's convenient, actually, with this notation. And then you have like three-legged tensors. And these guys, I mean, they can be, OK, what they're, OK, here for a vector, we have sort of it can be a vector, or it can be a linear form. If I swap this guy, here a matrix can be a vector in two copies or a linear form in two copies. For a three-legged tensor, you have a ton of possibilities. Either you are a vector in three copies, or you are a 2-to-1 linear map. Okay. You have many options, but let's write it as a vector maybe right now to confuse you. KLM. Okay. And so, okay, this is where this object here is a 5-legged tensor for me. This is where you all explode. No, it's okay. Okay, because if I identify, for me, I don't make a difference between Bra and Ket. I mean, this is just, I have 5 legs, okay? I act on 4 Hilbert spaces, so I have 4 Bras and 1 Ket here, okay? You'll tell me if you need more examples. I've not finished the tensor. I will finish the rules, and then we'll see if you get it. And okay, the rules. I mean, so if I put two tensors next to each other, I mean the product of the coefficients. Okay. So what I mean by that is that if I write this, what I mean is the object A, I, J, K, B, L, M. So if I did only that, that would be completely useless. I'm just drawing balls around stuff for no reason. And now the real rule is contraction. And there are two ways to explain it. Is that connected lines mean sum over a repeated index. So now if I write A, B like this, I connect them. Okay. This object is so this is sort of equivalent to the rule that if you have a line, the line is a special matrix corresponding to the identity. So this is equal to delta KL. We'll see on examples. I mean, you see two examples, you have understood, everything is simple. Maybe this is not the best way to formulate it. I'm totally willing to accept that. Okay. So examples. Okay, I'm going to make examples. The first examples, the notation is completely useless because it's too simple. But when things become complicated, you will see it's helpful. So if I have the tensor product of two vectors in tensor network notation, it's just U, V. Okay, actually, probably U star. Okay, if I don't care about the dual. Okay. Now if I have the matrix B applied to V, well, that's just okay. So you see, I'm already skipping writing the index here. I mean, this object is a vector now, so it has one index. It's here, and you could write it whatever. Usually we stop even writing the index. We understand that every leg that's open should have an index. We can do like the matrix A times the matrix B. There are two matrices, and this is just A, B. Okay. Now what we could do trace of AB. Then this is A, B, and like that. So you should always see if it matches, okay? The final thing is a scalar. So this thing should have no open leg. So it's a scalar, we're good. And that's, of course, you should do more than check if it's the right. But at least one sanity check is, does this thing live in the right space? Okay, so usually you should try to get a feeling of what's going on. And of course, where the tensor notation becomes interesting is that now, let's say you have I don't know, something like that, and that. I don't know, this is sort of visual and you understand what is connected to what. Okay, now you try to write this as a big sum with indices, you're dead. Okay, I mean, it's actually doable on this example, but it's painful. Okay.
So trace of A, you use B of loop.
A with a loop over it, yeah. Yeah, I went for the hard stuff already, but trace of A is A, like this. The thing also is, once you have tensors that have more than 2 legs, usually the natural operations you would want to do, they don't exist in linear. No one defined, you know. Let's say I have a 4-leg tensor and I start to contract some of them, okay? I mean, you can always write it as by fixing some indices, now seeing it as a matrix and imagining it's done on these indices, but sort of now with drawings, it's a bit clearer, okay? Yes?
For the delta KL,
Yes?
what did it mean?
I know, so what I just mean is that sort of every time you have a line connecting 2 indices, it's like doing, okay, I should say maybe sum over KL. Okay, not really, I don't mean the sum. I mean, when you start from a diagram like this, and now you connect them with a line, you're going to do sum over KL with delta KL. So you are forcing L and K to be equal.
So if you plug, for example, a vector to the KL, so it gives the vector?
Yes, yes. I think another thing is that in tensor network notation, what is the notation for the identity? That's what I mean, it's this. Okay, okay, we're doing the ultimate example and you're going to see where I'm going. What is the notation for psi L or maximally entangled state from before? If I wrote a vector, say like this, well, you could write it like this. But in fact, okay, topologically, I mean, this is just this, okay? So a maximally entangled state is just the identity if you see it, if you flip bra and ket. Okay, I wrote it here. Imagine I flip bra and ket, it's clear it's the identity. Okay, so all these gymnastics is kind of weird when you are at the state of writing sum with bra and ket, but this is sort of, this takes the burden away from you and you just see contractions. Yeah.
Always assuming that you're using the same basis, in particular for KL.
Yeah, this is very, okay, I should say. It doesn't have to be this way. You can be smart, make notations that are less basis dependent, but here it's like you have to see it from almost a computer point of view. Everything is an array, so everything is explicit. Everything is in a basis by definition. Yeah.
On your conclusion example, since there are no legs, this is a scalar. That's why you like.
This guy is a scalar. Okay, this guy is a scalar, but let's, and now it's a matrix. Okay, yeah. Okay. Okay, so I gave already one part. Now we're just going to rephrase what we did before in this language. And okay, I'm still gonna go in order. Okay, I'm not gonna go back to stuff. So. Okay, so what we just saw, I'm going to explain you why I say that a PEPS is a tensor network. And now, stop writing the weird stuff like this and write it in a more canonical way. So what we saw is that the psi L in tensor network notation is really just this. Okay, we had this, the drawing was similar, but this is a drawing that doesn't really mean anything operationally. It was just to give an intuition of a drawing. This now drawing in our notation means something. It's a tensor. Okay, it's a delta tensor. And now we have A. And so if you remember, A was CD okay? So it's a 5-leg tensor, and I'm going to write it this way. So this is A. And this is A, B, C, D. Maybe I should have taken colors, but I guess you understand. This auxiliary part is related to these guys. And the physical part, it's actually a pretty similar color that was in orange before, is here. Okay? But for me, I mean, it's also clear if you were ever to code A, it would just be an array with 5 dimensions. Yeah?
Can you repeat why psi L is the straight line, like the identity?
Okay, I mean, one way to see it is this way. Here, flip what's get on bra.
Oh, yeah.
Okay. So yeah, maximally entangled state is just the identity if you... That's useful, actually. Okay, so in fact, all the objects we used previously, we can use it to write our PEPs, psi of A, in tensor network notation. So I have to be a bit, what I mean by tensor network notation, again, you have to see that I am always identifying the state with the coefficients in its basis. So when I say what I'm going to write here actually is not psi A, but Ci1 In, the coefficients in the spin basis. But for me, that's the same, okay? This is probably not great in general, but right now that's what we're going to do. And what you're going to see is that, so let me put my tensors, A. I'm not going to write their other legs. Okay, let's put more. What happens, okay, is that every time we have a maximally entangled state, it connects 2 neighboring legs of A. Okay, so let me, I put the A's where they will ultimately appear. And the only thing my maximally entangled state says is that these legs are connected, actually. Okay, if you like, this is I1, I2, and here IN. Okay, this is where you have to focus. You should imagine this drawing keeps on. Okay, here this was a zoom on the drawing. Here it's still a zoom. You see that if I don't take care of what happens at the boundary, I'm going to have open legs on the boundary, so I'm going to have indices associated to the auxiliary states. So here I could either warp them around, so imagine that I have a pair connecting here back to here, in which case it would give periodic boundary conditions and remove these legs. Or I could just imagine, like I drew here, that there is no leg, that there's just no pair here, in which case the corresponding A acts on the smaller space. And so what that means, it has fewer legs, so it doesn't have legs on the boundary. Okay, so what I imagine here is that I drew the lower corner. Okay, and then my numbering is weird, but I drew the lower corner of the PEPs.
And the A are numbered.
So the A are, okay, I should say the A's here are all different, potentially. That's a bad notation, like it's A of X. They are potentially all different. But they are these tensors, yeah, so they contain, if you like, this is A, B, C, D, I. Okay, and sometimes we will put it here maybe, or I don't know, like to distinguish what is physical, but this has no meaning. Okay, this is just me writing it. It has no meaning as a covariant, contravariant, whatever. Okay, is this notation vaguely clear? So it is indeed now we have tensors on a network, so it's a tensor network. It doesn't go much beyond that. Okay. Okay, I'm not saying that this object is easy to compute. I'm just saying, in principle, this gives a recipe to compute it. Okay. On finite size, you could work very hard and translate this drawing into a computer program, contracting it and giving me the value for each coefficient. And here, okay, we forget a bit about everything that we've seen before of projected entangled pairs and how we have this pair that when we map, this is more for the intuition. If you didn't like this intuition, this can be taken as your starting point. Okay, you can forget about the sort of historical creation of this object, which I'm going to erase. So last questions about connections with the historical picture. This is now our tool. Okay, I erase. And now, so this is arbitrary dimensions. I hope it's clear here that you could easily do it 3D, 1D. Like, they have just more neighbors, and it becomes very hard to draw. But now we're going to do to 1D, which is going to become easier to draw. Okay. Okay. And now we're going to move to matrix product states. So for which the technology we developed of notation is slightly overkill, but later when we do algorithms, it's going to be super convenient. So it's worth the investment. Matrix product states, sorry, I'm confused with algorithms. Okay. So AKA 1D PEPs, TNS. But of course, okay, it's the other way around. MPS were invented much before, and the generalization came later, but okay. So, I mean, something I should have said before. What is, if you have a generic state, and its coefficients for me, it's the same as the state, Ci1, In. What is its tensor network notation for this object? Well, it's just a flattened potato, sort of like this, with I1 until In, C, okay? And it's a tensor with n legs. Okay, and that's why it's super expensive, okay, because the Hilbert space grows crazy. So MPS, on the other hand, MPS is, I mean, you just specialize this definition to 1D. So in 1D, this is the ansatz that this is, you are going to write it like this. Okay, this is I1. In. And this is with open boundary conditions. Okay, something I will not discuss too much is when should you choose open boundary conditions or periodic boundary conditions. Typically, the boundary conditions of your state should be the same as that of the problem you're trying to solve. Okay. And if we had to do periodic boundary conditions, we will just wrap around below. Okay, this is with periodic what else did I want to say here? Okay. So let's look at how, for once, let's go back to the original algebraic notation to at least show you that this thing is precisely the state I wrote before. So it's precisely the MPS that's used in the MRG. Actually, I lied because in the MRG you use open boundary conditions, but I'm going to assume this is this one that I wrote before as a trace of a product of matrices. Okay, so I have the A here is, if you like, KL, and it has this I here. Okay, this is the physical index, and these are the auxiliary indices. But now I'm going to write this as A, I, where this is not, so this is, if you like, I have D matrices like this. I'm going back to the old definition. Question for?
What is PBC?
Periodic boundary condition. I'm just going to say that now I'm going to look at the PBC case, okay? Okay, so if you like, I see it as a matrix like this, and this matrix has coefficients KL. Okay? So I'm going to write this like C, PBC. So you see that here, whenever I have two that are nearby, this really is, here I fix the index, it's an open bound. So what remains here is just the matrix product that we saw before. Okay, I'm summing the neighboring indices, so I'm going to have A, KL summed with LM, okay, and I sum on the middle index. So this is really a matrix product here. And at the end, I'm looping back the matrix product. And so I'm going to get the trace over. So this is really the trace of AI1 times AI2. And this is what I had advertised before. Except before, small distinction, I had only two matrices here. I'm allowing physical degrees of freedom that are Q dits. So I have D matrices. I have script D matrices. So if I go from a three-legged tensor to a collection of matrices, which I can always do, I see it, if you like, as a vector of matrices. Then I can write the coefficients, so I see I1, In, like this. Yes?
For the MPS representation, shouldn't you show the length of the A's on the right and on the left? Like each A should have 3 legs, no?
Yeah, each A has 3 legs, so you have 3 legs here and 3 legs here. Here?
No, for the MPS, just like
this one?
open boundary.
Oh yeah, so you're right that these, I will do open boundary just now. You noticed indeed that the boundaries are different. In this language, they are, so here I go from a 3-leg tensor to a vector of matrices. Here I go to a vector of vectors only because there are only 2 legs, okay? So I'm going to do the open boundary just now. But okay, why? I think it's easier to see the periodic boundary case first because all the sites are treated equally. Okay, here again, what you could add here is that this is A of 1, A of 2, A of n. That is, these tensors could be different in principle. Actually, in DMRG they are. Yeah, this is also something I wanted to say. Like that, sort of, the advantage of the translation invariant case is that it allows to go to the thermodynamic limit, but it's not fundamentally much harder to do not translation invariance, as long as your not translation invariance doesn't mean you are making some weird disorders that's going to make the system very hard to optimize or anything like that. But if it's some smooth non-translation invariance, it's sort of as hard from a bird's eye view. And so if you have C I1, IN, open boundary condition, here I'm going to be sketchier and you'll see if you understand. You have A I1 of 1, and these guys I write like this. It's a sort of vector for these matrices. A I2, 2. Okay, I don't know. I'm doing it more rounded to show that it's a vector in a different Hilbert space. That this is the auxiliary Hilbert space. Maybe I should do it sharper. I don't know. Okay. But okay, this is we have to get a number at the end. Okay. Is that understandable? Yes? I'm looking for no's. Okay. Okay, so we can look at examples. Since I don't have a ton of time, I will just give one. Okay, no, I will just give one. If I do periodic boundary condition and d equal 2, so like a qubit, like a spin 1/2 locally. If I take, I hope I didn't mess it up by the way, A0 equal 1, 0, and okay, what do I get if I do that? Question. What's the state?
Is this GHZ?
Yeah. This gives the GHZ state. Okay, so I don't know if anyone does quantum info stuff, but it's 0 plus 1. Okay. So as an exercise, you can try. So it's easier to do it with open boundary condition. What is W? So W is 1, 0, 0, plus 0, 1, 0. Okay, and you put the 1 in all the possible positions. Okay, this also can be written as an MPS. So this one I leave as an exercise. But it's not much harder. It's just very hard if you try to do with periodic boundary conditions, actually. So actually, many basic states we encounter, we could create easily. So they are expressive for typical examples. Okay, now there is a question that looks very difficult, and that's actually trivial. So it's very rewarding when we'll see the solution. How do you see that by increasing D, so capital D, the bond dimension, the size of these matrices, the size of this three-leg tensor, how do I see that I get everything? How do I see that ultimately I can cover the whole Hilbert space? Okay, maybe it's very expensive, but I can get everything, I claim. And in fact, it's a trivial statement.
Sorry, you're saying that with this representation, you can actually write every state in your
Yes,
space?
you can write every state, not economically. Okay, it's going to require colossal capital D, and that's not feasible. But the question is, at least we know that we are not optimizing in a subspace that cannot, in principle, reach everything. So it's not very useful practically, but conceptually, it's good to know that we can cover the whole Hilbert space.
You do something like capital D equals N?
No. You have to do D to the N. Yeah. Over 2 minus 1. We'll see. Okay? And the intuition is what? Okay? So, okay, I just want one point about what I mean. Is it expressive? Like, can we get everything in principle? And the answer is yes. So you start with your general C that I wrote like this, you know, before as a kind of flattened potato. And, okay. And then what I do, I will do. It's it's a disappointing thing. We will do something more smart. Now I write it this way. So no, I don't want to do it like that. This is a trick, okay? Like you're seeing that I'm doing nothing, okay? And this is already almost an MPS. What I'm going to do is here, I'm going to draw a ball here, one here, one here, one here, one here, one here. Okay? And now with this, what I mean by the ball is just the tensor network, the tensor corresponding to this. Okay, we saw before that a line is a reasonable tensor network. It's just the identity. Sorry, it's something that contains an identity in this direction and one in this direction. Okay, and maybe I draw a big ball like this around this guy that's doing all the heavy lifting actually. This and now this is this. So this is this is one of the most disappointing proofs in history. I think. There is nothing. Okay? And now I'm saying, okay, I can always group legs and declare that my Hilbert space is now the tensor, my new Hilbert space is the tensor product of the previous one. Okay? So I order the indices in lexicographic order and I define the new Hilbert space. So this is just this with this notation. And okay, I will. And what we could say is that this bond is fatter, and this bond is even fatter. Sort of the dimension is larger, but it doesn't care, okay, in terms of network notation. And it's a little less fat. Okay. Okay? Is that clear? Yeah.
But then you really need to allow for different A's in each.
Yeah. This is not translation invariant. Okay. I'm not assuming anything actually about the state here. And here, the D we need here at the worst point is D of n over 2 minus 1. Okay. No, that doesn't work. I should. It's what? N minus 1 over 2. No? Yeah, I think that's it. Yeah. Okay. Okay, so at the cost of exponential bond dimension, I can reach everything. Hey, that's good, because usually you work with ansatz that even in principle cannot reach everything. So, of course, here it's impractical to scale the bond dimension like this. In fact, if you go to such high bond dimension, you're essentially doing exact diagonalization in disguise, okay? But that's good to see that we can get everything. Okay. Okay, I'm not very fast, but okay. But at least I hope you understand. Okay, now what's important? Okay, we will go back later. Okay, this was to show that we can get everything. The question is, are we good at approximating what we care about? That's a more difficult question, and we will answer it later. Just, I'm going to do something simpler first, is to compute expectation values. And this is really a crucial point about MPS. That is not true in higher dimensions. Or that is not as true. Expectation.
Sorry, one
Yes.
question. I mean, so are you saying that basically, so the base of instance of tensor networks is basically complete? Is it a state?
It's not a basis. So what's important, I didn't show it, by the way. Okay, something I should have said. If you do psi of A plus psi of B, defined this way, it's no longer a matrix product state.
Yeah.
Actually, you can embed it in a matrix product state of twice, of the sum of the bond dimensions. So by making the A block diagonal, okay? So it's not a vector space.
Yeah, so what is the statement? The statement is just...
I'm saying that any state, I start from whatever state in the Hilbert space, I find U A is such that it's written as an MPS. There is no more statement.
Okay.
So I can reach everything if I make capital D large enough.
Okay.
But I'm not making statements about basis or everything because
No.
it's a tricky statement for things that are, in fact, MPS form a manifold, okay, not a vector space. So you cannot ask for more. Okay. So it's important because this question is important, and let's first the norm. That's a stupid question, but right now it's not clear. We will see next time ways to make sure the MPS is normalized, but right now we don't even know its norm. And so the norm is like the simplest of expectation values, okay? It's the expectation value of the operator identity. Yeah? Yeah.
And the upper diagram I want the periodic one. If we had capital D equals 4, then we have two lines in between each end.
No. One line is for capital D.
It's just that
Here the lines are D, small d.
okay.
And now I'm saying that if I want to fuse these lines in a single one, I need capital D to be larger, like to take into account that. Okay, so just we'll see that you will see that actually computing anything other than the norm is sort of the same thing, but it's going to be maybe slightly easier. One way would be the naive way. What is the naive way? Well, you fix the coefficients, I1 to In. You compute C. Okay, the norm is you sum Ci1 In by computing C. Okay? You get the thing? I mean, it's pretty clear that here I can, this trace is numerically efficient to compute. I have matrices. I can evaluate this at cost d cubed, okay, for each coefficient. But now if I do this sum, here I have exponentially many terms. So the naive way is what I call decompression. So you go from the matrix product state representation, you decompress it to get the coefficients, and now you sum the coefficients. That's bad. Okay, some approaches have no alternative. For example, neural network states, typically at the end you have to sample expectation values. But what makes MPS so good is that there is a smart way. Okay, I should say, really in general, knowing the wave function of a many-body system doesn't get you anything. Like the wave function, the state is not what you care about ultimately. What you're going to care about are expectation values. And expectation values are exponential sums over the wave function. And so knowing the wave function in many cases doesn't give you anything. Or say generically it doesn't give you anything. Then, okay, in some cases you have the wave function and it has a special form, and so you can say something. But in general, you cannot. And then in that case, we're going to have to do this in now matrix product representation. And so what I'm going to say, I'm going to write the bra first. This is A star. Let me do open boundary conditions. It's easier. I don't know if it's easier, actually. OK, I do one more. Okay, this is psi A and A this is the bra. Okay. What happens when I contract them? I sum over repeated indices here, so I just connect with a line. And this is good, okay? This is saving us. Why? Okay, let me actually take the new board. What notation did I use? So this looks like a ladder, okay? The left part of the ladder, I'm going to interpret it as a state, actually as a bra, like this, okay? That belongs to CD, tensor CD. Again, I'm a bit sketchy with the duals and whatever. When I have this, I'm going to say that I'm going to look at it as a map from left to right. So it's a map that goes from CD, tensor CD, to CD, tensor CD. And okay, there are 8. And the last one is just this guy. You get it by now. This is equal. I write this guy R, and again, it belongs to CD, tensor CD. And so what we have now is that with these notations, you understand that we can compute what this whole thing is a product of matrices T here, sandwiched with two states, left and right. So it's just, so the norm is just equal to L T. Okay, if T depends on, so T, there is an index here for depending on the site where it is. So it's T times T R. Again, here potentially the T, I don't write T to the n because it could depend on the sites. Okay. And what's the cost of computing this? So you have, I mean, okay, even roughly asymptotically, the cost is ND4. Yeah, ND4. However, this is a lie because there is a way to do it a bit smarter. Sorry? Yeah, so okay, this is going to help you solve the n, but I don't care. Okay? What is going to happen in the term, I'm foreshadowing some stuff, in the thermodynamic limit, if you take all the t the same, for a very large system, you do translation invariant approximation, then this is going to converge to the fixed point of t. And so the only thing I need is to know the leading eigenvector of t. In fact, I don't even need to know the full thing. So I can make this dependence in n disappear for n large, so paradoxically. So when n is very large, it no longer depends on t. It becomes a constant. But actually, this d4 can be brought back to d cube, okay? Because I was sketchy, but sort of the way to apply t to a vector naively scales like the square of the dimension of the space. But this usual trick we have for the Lindblad. This acts like a Lindblad operator in a way. So you can see that you don't sum over this, then this acts like matrices on the left and right of the vectors, and you can go down to d cube. Okay, this doesn't matter at all. The whole point is that it's polynomial. It's very cheap. Okay, there is no exponential in that stuff. Let's say you take d equal 100, an MPS of reasonable size. and in a matter of hundreds of milliseconds, you get your result. It's not going to sum exponentially many terms, and it's exact. Okay, so this state is has exactly computable expectation values. Okay, I sort of check what I have. Yes?
So in general, it would be ND cube?
Yeah, in general, it's ND cube, yeah. Sorry. I mean, ND cube, and if you are translation invariant, you can kill the N. It's clear that if you're not translation invariant, it's going to be very hard to not scale with N. Okay, like even with the best method in the world. Okay, so if you're okay, I keep on for 10 more minutes, and so that. So I wanted to start the explanation of why MPS work, but I will start that next time with the algorithm. So I'm sorry, we will not have that, but I want to very slightly generalize what we just did. What happens if now we want to compute something like this? I should say maybe x1, x2, where x1 and x2 are two lattice sites. And this OX is an operator, let's say to simplify, that acts on only one site. What that means in tensor network notation is that this OX, okay, I put a hat, I don't know why, is equal to the identity everywhere, and maybe, okay, O is not a very smart name, but okay. And this is at the X position. Or in the usual notation, that means that it's the identity, tensor, tensor, O, tensor, identity, tensor, identity. Okay? This is like to test your understanding of the tensor network notation. So what is this guy? It's just a ladder where two steps are weird. Okay, so let me write it in compressed form like this. And now I will start doing what everyone is doing, because I will stop writing even the A's inside the balls, and we'll sort of remember that it was A star on top and N star on top and A below. What you're getting is something like this. Okay, let me. And maybe here, you have O. Okay, and I'll put it here. And this is x1, and this is x2. Okay? But now I can just define this object, this modified T. Okay, usually T is called the transfer matrix. I should have said it. So I define a modified transfer matrix, TO, like this. And it's just the same as before, except I will insert TO when now there is an operator. Okay? So the complexity doesn't change with before. So now it's the same as before. I'm saying it's not more expensive to compute the expectation value of operators. So I still require something here. I require that the observables I'm computing are decomposed into approximately local things. Okay, so let's say now I have a fully generic operator. A fully generic operator is going to be like it's going to be a two-sided potato like this. Okay, and now if I insert a two-sided potato here, I'm dead. Okay, there is no way I can contract it. So if I want to be able to contract it, they have to be local. Okay, if it's two sides, it's okay. I'm just going to have to define a slightly bigger t that I'm still going to be able to compute, but it should not be crazy large, otherwise I will not even be able to define t in the first place. Okay? Okay, well, I should say, okay, we'll see later. But in practice, you don't even write down the matrix T. You just look at how it acts on a vector. And so I just want you to understand that in principle, once we have a state, we can compute expectation values on it. We can compute expectation values of this form. That includes, in particular, local Hamiltonian. So we have all the pieces to optimize it. So given a Hamiltonian, we could find the best approximation to the ground state with fixed bond dimension, for example, by doing gradient descent over all the A's at the same time. Turns out it's not super efficient to do it. There are better techniques, but like philosophically, we have everything that's needed right now. Yes?
Just for the scaling, if I had I wanted to take a void with an operator which take, for example, the state and two neighborhood, I will add the number of neighborhood I need in.
Yeah, you're right, you're right. So I discarded the scaling in small d. Okay, so here indeed you have to, just to define t, you're going to have a sum. Here it's going to involve a sum over the physical coefficients. So in fact, the cost d appears back there. Okay, I just gave in small d, in the physical dimension. So indeed, what is going to happen if you start to act on more sites, you're going to have a small d to the power number of sites, and then you're going to hit an exponential cost. But okay, since typically d is fixed in your system, it's not something that scales. I didn't put it here, but you have a d here, actually. And in fact, algorithms would have algorithms for optimization typically have a d squared, that they can have some fixed order cost in d. But okay, in practice, d is something small. Let's say you're studying a spin chain, like small d, and capital D can be huge if you really want to be super precise. So it's really the scaling in capital D that matters usually. Although I say that, and you know, for bosonic systems with very large Fock spaces, it could start to matter actually taking care of these subleading scalings that no one cares about. I don't say no one cares about, but they are really secondary usually. Okay, so before we leave, so I will on this part we will keep on next time by seeing why MPS are efficient at approximating states with the area law. So far it's just intuitive. You see that if we cut the system in two, we cut a small number of legs, and so the entanglement entropy is finite, but we're going to make that more precise. And yeah, so I want to show just very quickly matrix product states in the wild. So that's a bonus in a way. Okay, just before I go to the bonus, it's clear that we have all the pieces in principle to solve a many-body problem now. We have a class of states, and we know how to compute expectation values. I could even compute gradients by finite differences. Okay, that doesn't tell me it's going to be efficient, but in principle, I could. Okay. Yes.
Just to be sure, here on the gadgets on the right, there are no stars on the bottom ones.
Ah, no, I messed up here. You're right. Okay, there is no star on the bottom ones. Yeah, sorry. I'm too lazy to go back there. So bonus MPS in the wild. So that's to. I know many of you are doing more quantum optics, understood in the very broad sense of quantum optics, in the wild. And at least in the group, Quantic, I don't know, one talk out of two has this experiment of Arosh and collaborators, so I have to have it. Okay? Consider a cavity with light. So you have light in a cavity, okay? And then you see the Rydberg atoms inside the cavity. I'm literally doing the Arosh experiment. And really sorry for the et al. That has 1 million very good people. Okay? And so here you have a Hilbert space, H cavity, which we are going to say we are going to truncate. Okay, in principle, the cavity is infinite. We're going to say it's C, D, and oh, mystery, capital D. And I'm imagining my Rydberg atoms here. They live in a Hilbert space called CD. Okay? And when they go together, you know, there is an interaction between photons in the cavity, so this Hilbert space, and the Hilbert space of the Rydberg atom that's inside. That takes the form of a unitary operator. So I'm sketchy, but sort of every time a Rydberg atom enters the cavity, there is a unitary that acts on this copy of the Hilbert space and the cavity. Okay? Initially, all the Rydberg arrays are in a product state, and then they enter the cavity. And usually very late they are measured, but I'm going to assume that they fly. Okay? I'm creating a chain of Rydberg atoms. And now these atoms, they are no longer in a product state. Okay? Because sort of the first got entangled with the cavity. This sort of shifted the state of the cavity, and now the cavity interacted with the second one. And this way, the first and second one got a little bit entangled, okay? In what state are the Rydberg atoms after they interact with the cavity?
The maximum entangled state?
No. What? They are in an MPS of bond dimension D, capital D. Okay, and it's very easy to see, actually. So the initial state, actually, no, it's even stronger than that, but I won't prove it, that you could create any MPS this way by tuning the unitary here. Okay, this is my cavity. So that's the vector, the initial state, cavity, initial state. Okay, this is how I'm drawing it. So it's a vector, so it's a ball and with a leg. And I do like before, now I stop even writing what's inside. Okay, that's the state of the cavity, initially. And now I'm going to write my Rydberg states like this. So that's the first one to interact and the nth one. Okay, so first one is here, and in this drawing, the nth one has not yet interacted. What I need is a unitary. And so my unitary, I'm going to write the two ingoing legs. So this is cavity in. This is Rydberg in. And this is Rydberg out. This is cavity out. Okay, so I'm just writing a unitary operation. A unitary operation that acts on two Hilbert spaces is a thing that has four legs. Okay. The legs were, so I'm going to put the vectors here, and it's going to split two vectors here. That's clear? So now what happens? First, I do an interaction like this, up, up. The cavity state keeps on, and the Rydberg state keeps on its way. Now the cavity re-interacts with a new thing. You get this. And here. Okay, now what you can do, and then it's, okay, you can be a bit smarter than that, but you can maybe post-select. So you can measure the cavity in a certain state at the end. If you post-select, it's going to do this. You're going to measure a certain state. So it's like making the scalar product. Okay, for the cavity, I'm killing the last index. And now I'm doing the same tricks as before. Okay, this I declare it's, okay, actually I will even include this guy. That's one box, that's another box, that's another box. And so at the end, what I get is something like that for the state of the Rydberg atoms. And sort of as expected, the amount of entanglement that they can share is proportional to the bond dimension, and thus proportional to the effective dimension of the Hilbert space here. Of course, U has to use somehow this bond dimension, okay? It has to use this dimension. So it's, when I say the dimension here tells you the amount of entanglement. It rather tells you the upper bound on entanglement. So it doesn't have to saturate the D. Okay, so the state of the Rydberg atoms after interaction is an entangled state, and it's a matrix product state. In fact, this has been proposed in the literature as a kind of way to test some proposals, or to say you simulate many body systems with a single cavity and Rydberg arrays. Of course, you don't simulate anything non-trivial precisely because this thing is a matrix product state, and so we know very well how to deal with it. Conversely, you can understand why can we deal with MPS so easily, because they are equivalent to this cavity problem, which we know very well is easy to solve because it's a Markovian system with repeated interactions, and solving it is trivial. So understanding, say, computing expectation values for observables on the Rydberg atoms is very easy, because they don't talk to each other once they have interacted. Okay, so that's all I had to say. You see, even MPS in the wild, it's like in an experiment, but that's an exact MPS in that case. Okay, next time we understand why it's so efficient and we see algorithms.